What's up, everybody? Welcome back. Patrick here. Moving on to the next question. So let AB be any point on the graph f of x equals 1 over x. We have to prove the triangle area formed by the tangent through AB and the coordinate axis is 2. This question is pretty difficult, one of the more difficult ones you'll get in this unit, but I'm going to do my best to explain it. So the first thing I'm going to do is I'm going to draw the graph 1 over x. The reciprocal function, if you remember, just looks something like this. And for this example, I'm just going to ignore this part of the graph. I'm going to work with this here. So what they're saying is that there's a triangle formed when you take a point on this function. So the point is AB, and if you draw a tangent through it, tangent's going to look something like that. So the triangle formed with the tangent and then the coordinate axis, we have to prove that the area of this triangle is going to be 2 every time. So how can we do that? Well, if you think about it, area of a triangle is what? Base times height divided by 2. And the base of this triangle is just going to be this line right here, because this is a right angle triangle. So this here is going to be the base of the triangle, and then this here is going to be the height of it. So this is the base, this is the height, and the base is basically going to be the length, the same number of the x-intercept. So for example, let's say the x-intercept is 5 and 0. Well, the distance from the origin to that point 5 and 0 is just 5. And then the height is going to be the same number as the y-intercept here. So let's say the y-intercept is, I don't know, let's say 0 and 11. Well, the height here, the distance from the origin to that point is just 11 units. So in this case, the area would be 5 times 11 divided by 2. So instead of using these made-up numbers that I put here, we have to find general expressions for that x-intercept and for that y-intercept. And the way we can do that is we can just figure out what's the equation of this line going to be, of this tangent line. So how can we do that? Well, first off, notice that they mentioned that the point is a and b, but because we have a defined function, 1 over x, and this point a and b is on 1 over x, then instead of putting b, notice how we can make the y value in terms of a as well, because at an x value of a, the y value is going to be 1 over a. So instead of having a b value, I say we just put 1 over a. Whenever you can make stuff in terms of one variable, it's always better, right? So instead of a and b, the point on the function 1 over x is actually a and 1 over a. Right? So we're going to have to get some kind of equation for that tangent line y equals mx plus b. Now, let's start off with the slope. How can we find the slope of this tangent line? Well, we can take the function f of x equals 1 over x, and we can find its derivative. So f of x equals 1 over x, we can rewrite that as x to the negative 1. And if you take the derivative, apply the power rule, bring the negative 1 down, and then subtract 1 from the exponent, you get something like that. So the derivative is negative 1 over x squared, like that. So this here gives us the slope of the tangent at any x value. Well, we want the slope of the tangent at this x value of a. So we know f of prime a, if we plug in a for the x value in the derivative, it'll just be negative 1 over a squared. So for any x value a, the slope of the tangent is just going to be negative 1 over a squared, right? The slope of that tangent line. So going back to our line equation here, we know that the general format is going to be negative 1 over a squared x plus b, right? Where this bracket here is the slope of that line, of that tangent line. Well, what do we usually do? We get the slope, and then we have to solve for the b value. So to solve for the b value, we have to plug in something for x and y, basically a point on the line. Well, a point on the line is just going to be this point a and 1 over a. So we could plug in 1 over a for y, and then we can plug in a for x, and then we can solve for b. Well, notice here how this a and one of the a's at the bottom will cancel out. So we'll just be left with negative 1 over a, and then we have to bring that over because we want to get the b by itself. So we'll have 1 over a plus 1 over a. 1 over a plus 1 over a gives us 2 over a. That is the b value. So the equation of the line, this tangent line here going through a and 1 over a, and that point being on 1 over x, it's basically y equals negative 1 over a squared x plus 2 over a. This here is the equation of this tangent line. And now notice, since we have the equation of the tangent line, we can find the x-intercept of that line and the y-intercept. So the easier one to do is to probably find the y-intercept first. And actually, the y-intercept is just the b value, because if we plug in an x value of 0, that's how we always find a y-intercept. Plug in 0 for x, this times 0, that would go away, so we'll just have y equals 2 over a. So we know the y-intercept is going to have a coordinate of 0 and 2 over a. So this coordinate here is 0 and 2 over a. Right, so that is the y-intercept. Now what about the x-intercept? Well, for the x-intercept, we have to plug in y is equal to 0 and then isolate for x. So we plug in 0 for y here. So we'll have 0 equals negative 1 over a squared x plus 2 over a. Right, so let's maybe bring this negative or this positive 2 over a over, and that'll be negative 2 over a equals negative 1 over a squared times x. Then to get the x by itself, divide both sides by negative 1 over a squared. Like that. Right, so maybe doing this up here, x is going to equal negative 2 over a. Notice how we're taking a fraction, dividing it by another fraction, so we could just flip this second fraction. So we'll be multiplying it by a squared over negative 1. Negatives cancel out, become positive, and then an a and one of the a's up there cancel out. So multiplying everything together, we end up getting 2a. Right? So the x-intercept is going to have a coordinate 2a and 0. So this point here is going to have a coordinate 2a and 0, like that. Right? So we have the x-intercept and we have the y-intercept for this tangent line here. Y equals negative 1 over a squared x plus 2 over a. And just as a recap, how we got the slope, we know that this point is going to also be on the function 1 over x. So to get the tangent slope, we took the derivative of that and then just plugged in an a value. Then to get this b value, we plugged this a value and this y value in for x and y, and then just solve for b. Then once we have the equation of the line, we could find the y-intercept and the x-intercept by plugging in x equals 0, y equals 0, respectively. And now, if you remember at the beginning of the video, I said area of this triangle is going to be base times height divided by 2, and because it's a right angle triangle, the base is just going to be this value of 2a. So we'll have 2a, and then the height, I mentioned that is just going to be the y-intercept. So the height of the triangle is going to be 2 over a, and then we're going to divide it by 2. And then notice here at this step how the a's will cancel out, right? We have an a in the numerator, a in the denominator. Those cancel out. 2 times 2 is 4. 4 divided by 2 is 2. So that is the area of the triangle, and that's what we were trying to prove. Right? So fairly tricky question. You basically have to get the equation of this tangent line all in terms of a. So one of the first tricks actually was to change that b value to 1 over a, since it's on the function 1 over x. And then, yeah, once you get this equation of the line, find the x-intercept, find the y-intercept. X-intercept's your base, y-intercept's your height. Multiply them together, the a's cancel out, so the a's are sort of irrelevant. So 2 times 2 divided by 2, 4 divided by 2 gives us an area of 2. So that's going to be the area of the triangle that's always formed with a tangent line on 1 over x and the coordinate axis.